All right, it's time to get into the fun part of this course. We're going to talk about generative modeling. This is the technology behind all those viral apps that let you swap faces around and age people and stuff like that. Also, the technology behind deep fakes, kind of a poster child of the ethics discussion we had earlier in the course, but I'll spare you my rant on that for now. Before we can talk about generative adversarial networks, though, which is the tech behind all that stuff, we need to talk about variational autoencoders, which is the underpinning of generative adversarial networks. So let's dive into VAEs first. Before we talk about variational autoencoders, let's first talk about autoencoders in general. This is kind of a diagram of how they work. So an encoder learns how to reduce input down to its latent features. So that's kind of the left side of this diagram here, the yellow part there. So basically we take an input, which is often an image, and by using convolution, just like we saw in convolutional neural networks, we distill that down to some sort of representation of the latent features or latent vectors of that input signal. So our encoder there looks a lot like a CNN. It's using convolutional layers and max pooling and all that stuff to sort of distill down the patterns in the input that we're training it with down to these latent vectors that we're representing here as the blue Z box in the center there. So nothing really too new there. On the other side, though, we have the decoder, which is basically the inverse of the encoder. So it's being trained on how to reconstruct complete images or complete data, more generally, from those latent vectors in the Z box there. So by using transpose convolutions and max depooling and things like that, it learns how to take those latent vectors and reconstruct them into a full complete image or a full complete data set. So while we're training this, the objective is to try to get the input and the reconstructed input to be as similar as possible. That's what we're trying to optimize for there. So x should be about equal to x prime, where x is the original input images that we're training it on, x prime are the generated reconstructed images based on those latent factors, those latent vectors that we've learned through the training process. So pretty interesting stuff. Now the system as a whole is trained such that the original input fed into the encoder is as close as possible to the reconstructed data generated by the decoder. What I just said, but let me try to make that a little bit more real with an example, right? Let's say that we're training this on pictures of shoes, all right, just to pick something out of the blue there. So the encoder would distill that down into sort of the essence of what makes a different kind of shoe. And it's not going to be thinking about it in these terms, it's just a neural network, right? But what those latent vectors might ultimately represent is this thing kind of fits the pattern of a sandal, and this other thing kind of fits the pattern of a sneaker, and this other thing kind of fits the pattern of a boot that I've learned. It doesn't know how to label them or to call them those things, but that's what it might learn in those latent vectors in the Z box in the middle there. And the decoder will learn how to take that and reconstruct a complete image of a boot or a sandal or a sneaker based on that latent vector there. And, it could be more to it than just a classification, right? I mean, a very simple latent vector would just be a classification of what kind of shoe is this, but we can have more information in there that's more nuanced. And that's kind of the beauty of the system. It's a little bit more flexible. And once we've trained the whole system, we can actually throw the encoder away because we just use it for training the decoder, really. So if you want to just generate synthetic images of different kinds of shoes, you could use the decoder to do that. And the idea is, you can generate a bunch of synthetic generated pictures of sandals or sneakers or whatever it is at random if you wanted to. And that's kind of where the underpinnings of all these sort of, fabricated faces that you see on viral apps comes from. So there's a lot of applications to this. I mean, going back to the ethics discussion, nobody really intended this to be used for deepfakes or deceiving people, right? The original goal was actually for compression. So you can think of this as sort of a noiseless way of compressing data down. So if you want to have a really clean way of saying, I just want to have a picture of a sandal, here's a way to do that with just, basically a few bytes of information potentially, where it learns how to reconstruct that without any noise. Also, it can be applied to dimensionality reduction, obviously, kind of the same thing as compression. We're taking that higher dimensional input and boiling it down to those latent vectors there instead, to a lower dimensional representation. It also has applications in search. So we could use that to sort of distill a corpus of text data down to its relevant search terms. Denoising, the decoder can be used to reconstruct an image that has no noise in it based on an image that does have noise in it. That's another good application of it. I use that in Photoshop all the time, actually. Or colorization is also a cool application. Maybe this thing can be trained to recognize that this picture of a person looks like he's wearing a pair of jeans in this black and white image. And based on the shape and the shade of gray in that image, we think it's a pair of jeans, and maybe I should color it blue because most jeans are blue. So, again, it's not thinking about it in those terms, but those are the labels that we might attach to what's going on under the hood there. So again, the trick for doing this in the decoder is to use a transpose convolution instead of a convolution. So instead of conv2D layers, we're using conv2D transpose layers to reconstruct images from those latent features that we talked about. So it's going to be learning all the weights used to create a new image with new pixels from a lower dimensional representation. And again, it can be used on more than just images, like we talked about. Search and text information is another application, but images are kind of the easiest example to wrap your head around here. So with a transpose convolution, we're not distilling things down or shrinking images down, we're actually expanding them into their original form. We're trying to. You'll often see it used with a stride of 2. I've also seen some decoders where they sort of intersperse strides of 1 and 2 at different layers if you need more complexity, but you'll probably see a stride of 2 in there somewhere. And again, if you're we're going to be using max unpooling instead of max pooling, like we talked about when we talked about convolutional neural networks. So think of the decoder roughly as a CNN that works backwards. It's kind of a good way to wrap your head around it. So let's talk specifically about variational autoencoders. What do we mean by that? So in a variational autoencoder, those latent vectors are probability distributions. And this is a way that we might graph those probability distributions for a given, given set of categories or what have you. So we represent those probability distributions by the mean and variance of Gaussian normal distributions. So a variational autoencoder is specifically using Gaussian normal distributions and the properties of those distributions as its latent vectors that it learns over time. Mathematically, we can express it like this. The input data x is expressed as a probability of z given x, where z are those latent vectors, and then we can reconstruct z using the probability of x given z. So flipping that back on its head to reconstruct the original image. And this is the inspiration of generative adversarial networks, or GANs. So we're getting there soon. We'll see that GANs are just another spin on variational autoencoders where it's more general than using Gaussian normal distributions. One thing that you're going to see in the code that we should talk about is something called the reparametrization trick. I'm not going to say that again because that's a tongue twister. So one mathematical problem with the idea of VAEs is that the probability distribution that we're calling Z can't be differentiated. Anytime you have randomness in the equation there, these random distributions, that throws a wrench into the calculus, right? And as you might recall from when we talked about training neural networks, we need to use the derivatives of the system for backpropagation and the actual learning to work, right? So the trick we use to get around that is by converting the random sampling in Z to a deterministic form. So mathematically, we might call that Z equals mu plus sigma times epsilon. The specific Greek letters you use don't matter. We're actually using different ones on the diagram here, but the idea is that we're introducing this new epsilon term, or whatever you want to call it, where the randomness gets moved off to. So epsilon is the random variable from the standard normal distribution here, and by pushing that out into its own term, that pushes the random step out of the network as an input, and then we can have a connected graph again that we can actually differentiate and actually do training on and backpropagation. So I'm not going to get into the math of that too much. I just want you to know what that is. Also, in the subject of things you just need to know what they are is Kullback-Leibler divergence, or KL divergence for short. This solves the problem of measuring the distance between two probability distributions. So what we need, as we're training, to measure the distance between the probability distributions of our original data and the reconstructed data. We want those to be as close as possible, right? And one way to measure that is KL divergence. Sometimes they call it the Earth mover distance because of an analogy used of how much Earth would you need to move to transform the United States into the shape of the United Kingdom. I think that's the actual example used. But a simpler way to think about it is this diagram here. Let's say we have a shape of 3 stacks of 3 blocks. It's basically how many blocks do I have to move to get it to look like 9 stacks of 1 block, right? So it's just how much information do I need to move around to make these two distributions, these 2D graphs, line up with each other. Mathematically, it looks like this: the sum of p of x times the log of p of x over q of x, which is equivalent mathematically to the cross entropy of p and q minus the entropy of p. So we sometimes also call this relative entropy. And as you might recall, entropy is a really common loss function. So it means we can use this as a loss function while we're training our variational autoencoder. And further, we can decompose that as this function here. I'm not going to get into the mathematical derivation of that, but when you see that function, this is where it's coming from. That is the Kullback-Leibler loss function here, expressed as you might see it in TensorFlow. So with that, let's dive into a notebook and see how VAEs actually work.